Okay, so I hope I am audible, and today is the first lecture. We are going to look at the introduction of the formal methods. If I have to say, or I have to tell a layman what is a formal method, basically it's a simply use of mathematics in the software system development or hardware system development. That's all. We generally say that we become true engineers by the use of mathematics. Okay, so software engineering or computer science is also supposed to be using a lot of mathematics. For what? For conciseness, for precision, for correctness. Okay, so that the software designed for a particular purpose are going to fulfill its purpose rather than they are going to fail. Okay, so that's basically where formal methods are going to help any computer scientist or software engineer to develop the better software. First thing. Second thing, actually, I would say like as far as your career is concerned, there is a difference between pay and perks. If you know the formal methods are mathematical techniques to prove that your software is going to be correct or your software is going to work as it is desired by the customer or as it is desired by the client, then probably you are going to be valued and paid more than who doesn't or who cannot ensure that whatsoever they are going to deliver is going to work as per the specification. So keep in mind two things. For being a real engineer, you need these methods, that means mathematical techniques, and also for better perks and better salary, you are supposed to learn this particular subject or this particular method. Okay, so I would only say that these are two reasons. These two are very big reasons as per my opinion. Okay, so in formal methods, our focus will be over the modeling. Okay, so how we are going to model a systems. Probably you remember from the object-oriented modeling course where we defined model. Model is nothing but a description of a reality. So if you remember, and why we describe reality and what are the various aspects of modeling. So you can recall or you can just look back at that particular object-oriented modeling course. Why do we model and all those things we have already done. Okay, so why do you model and what is a model? Model is a description of reality, and why do we model is basic reason is basically uh, it's going to be unambiguous description of particular thing or something which we are going to do. We will see in this course also various models and why we are going to model. So modeling will be the focus. Then further hands-on approaches towards formal verification. That means today itself I will try to make you enable to write a certain small programs in certain language by which you are going to do verification, because there is a lab course associated with this particular course. So you will be given certain examples which you are supposed to be solving into your lab in your labs. So small examples, probably by the end of this class you will be able to see how very small example we can try to solve as far as the verification problem is concerned. Okay, so definitely we will be focusing on practical usage of verification rather than very theoretical. So we will go in theory also little bit, but as much is required for understanding of the practical applications of the formal verification. Okay, So as I said, you will be applying this formal method in your lab. And if you are actually going to do the lab and you are going to attend the regular, you are going to attend the lecture regularly, then probably you will enjoy this course. And mostly we will be looking uh, as a modeling language, either finite state machines, which you have probably already done into automata theory course or formal languages and automata theory course. So we will see like we can build a model by the use of finite state machines, be it DFA, deterministic finite state machine, or be it NFA, but we will not focus much on this. The language which we are going to take is CCS, that is a process algebra, which through which we can model a concurrent communicating systems. And we will see like most systems which we deal with nowadays are going to be concurrent and interactive systems. So CCS and pi calculus are going to help us in modeling the concurrent and communicating systems. That basically we will be trying to use this. Other than this, we will be also looking at a new assembly tool. Okay, so and it's a theory and applications. Theoretical background on temporal logics and model checking, we will see. I will start how to build the model and how to write a formula into any logic or very simple logic. So that's the objective of today's lecture, as well as this will be the objective for whole of the series of the lectures which we are going to look at. Okay, so textbooks, as far as the readings are concerned, there are going to be certain textbooks. So communication and concurrency by Robin Milner, and then pi calculus is also by Robin Milner. These books are available in the library, but probably you don't have access. So these books are also available online on the net. If you can find them, search them, it's a good. So all these books which has been mentioned over here, like Logic in Computer Science by Huthanian and Model Checking by Clark, Brumberg, Pellet. Okay, so all these books are also available online on some websites, so you can download them. Otherwise, I have these books. On your request, I can actually send you by private emails. I cannot upload these books on the website. Okay, so due to copyrights and all those things, you all know. But if you need it, just mail me. I'll send you all these books through mail. Okay, and then you are supposed to look at the lecture slides. Assessment criteria, and as far as the workload is concerned, for this course, actually, you know, mid semester is going to be 20%, which will be based, if the classes are going to be online, on the quizzes. That is the you will be given and you will be submitting actually. So 10 marks for the class quizzes, that will be a surprise quizzes, and 10 marks for the assignment. There will be 5 assignments. And then motivation for this course, I already told you 2 motivations. That is better pay, and second, to be a true engineer. But another motivation has been given by a scientist, that is the farmer Almank for 1978, that to err is human, but to really foul things up requires a computer. Okay, so we will see like that there has been many mistakes which actually has been done by the human being, but mostly computers are supposed to be responsible for that because of computer, though these mistakes were human mistakes, but as they have been carried out, those operations has been carried out by the computer, it has been dedicated, or it has been made responsibility of the computers, because of the computers this mistake actually has happened. That's not fair, but still we say. And then we also see that Nancy Levinson saying 60% of all major industrial disasters from 1921 to 1989 occurred after 1975. And even till now, computers assist us in many ways, makes us do a lot of things which we cannot do without the computer. But at the same time, we all know that they are responsible for many bad things also in our life. Okay. So, and I need not to probably elaborate the misuses of the computer without, if you are going to not use it properly, or if we are not using security, safety, and all those things, then what may happen? Being eighth semester of the computer science, I hope you all are well aware about its disadvantages also, rather than advantages only. Okay, so software systems, as we say, these software systems are everywhere nowadays. Okay, so if you look at the wristwatches, washing machines, microwave ovens, elevators, mobile telephones, so whatnot, like everybody is using smartwatches, isn't it? And you know, you better know than me that you are actually calculating how much calorie, how much steps you have taken. Everything is being monitored. Okay, so there are going to be the softwares in those devices. If there is going to be error in that particular software, then probably we know that there could be disasters, or there could be problems due to all those mistakes. Okay, so along with this, there are going to be the safety critical systems also, like aircraft, trains, nuclear and industrial plants, avionics, life support systems. Okay, so you all know, like nowadays, metros, there are going to be no drivers, they are fully automated. Only drivers are sometimes sitting there just to make people feel that it is being driven by the driver. It's not fully automated because okay, and you might have heard about the autopilot mode in case of the aeroplanes, where if plane reaches to the certain height, then it goes into the autopilot mode. There is no interference by the pilots most of the times during the flight. And once it has taken off, okay, or once it is landing, then only once it is taking off or once it is landing, then only they have to be careful. Okay, so life support systems. So in all, if we say that quality of life is going to be equated by the quality of computational systems. If uh, as far as you people are new generation is concerned, you might be knowing, like you might be using the devices every day, and even if a particular device doesn't work for a day, you are going to wake up in the morning, then how much worried or how much troubled you people are. Okay, and then the life is also going to be on stake. Okay, so how actually error takes place, we are just going to have a pretty simple example and look at it, that even if there is going to be a lot of intelligence in human being, but sometimes actually mistakes may happen, and there has been a lot of mistakes in the past also. Okay, so in the design, supposing as I said, it is going to be that aeroplanes are going to be into a autopilot mode, and then supposing there is certain parts which has been written for avoiding a collision with other planes. Okay, so what has been written, supposing the logic is something like when two planes are at the distance less than 1 kilometer. Okay, then they are going to actually, at the distance of 1 kilometer, they are going to give warning to other plane and notify the pilot that there is going to be another plane inside of this. And whenever there is going to be distance which is actually the 300 meter away, and no changes in the course of the other planes were noticed, then go up to avoid the collision. So this is a pretty simple logic. Two planes are coming, and if one plane is going to give the instruction to other that you are in my sight, and it sees till it reaches to 300 meters, then it goes up. Okay, but the problem with this solution is pretty simple solution. You all might have guessed, if the same software is going to be there into both the planes, then in that case, what will happen? Both the planes are going to go up, and eventually both of them are going to crash. Okay, so it's a pretty simple thing, just very obvious logic. But when we will deal with the software, then we will see like there have been certain errors which has happened, or certain behaviors which has taken place, and which could have been avoided had the people used formal methods or mathematical techniques to prove the system correct. Okay, so this is one thing that is why it generally happens, that you cannot predict all the behaviors of any system. Okay, as you see, US aircrafts went to southern hemisphere and flipped when crossing the equator. So supposing you have somebody is into the northern hemisphere, and every coordinate and everything has been computed or has been done as if this plane is going to always fly into the northern hemisphere. Then if you are going to be into the southern hemisphere, then you know like what will happen, because in southern hemisphere there are going to be calculation of the coordinates differently. Okay, and in northern hemisphere these calculations will be different. Okay, so it's in the initial days, people say that softwares were such, when it crashed, the plane flipped and crashed, and then later on they thought why the accident took place, and then they modified the software. And software written for US F-16 fighter plane. Okay, because it is generally supposed that altitude for any fighter plane is going to be higher than the sea level. But in the case of the Dead Sea, altitude is going to be the less than the sea level. When it actually flown over the Dead Sea, there has been accident. Okay. So these are the things which are going to be there, which cannot be predicted beforehand. But if you are going to model the system, and then if you are going to verify it, or if you are going to prove its correctness, then probably you can catch it. So no guarantee that all behaviors can be predicted, but we will see there are many which can be actually predicted, and which can be actually corrected. Okay, so these are certain accidents, you can say bugs were there, are design faults were there, are modeling issues were there into the system, so which actually can be deadly or costed a lot. Okay, so what were these? One is the Thirag 25 accident. This was a simple Thirag 25 machine was there to cure the cancer patient just by giving a high dose of the X-rays. Okay, due to certain uh, bug in the software, it actually causes the wrong doses of X-rays, that very high dose of X-rays, and then many people died in the US. And that bug was also something like could not be replicated, because there were concurrency in the system, and this bug was basically very difficult to reproduce, because only after certain settings it has happened. So in 100 cases or in 1,000 cases, one person is going to lose a life. Okay, but finally they found it that there was an error in the software system. And then Ariane failure in 1996, Ariane 5 rocket actually exploded. just after 40 seconds. It was a pretty simple exception which has been thrown and which could not be caught, and then system behaved differently. That's all I can say at this point of time. So this is this costed $400 million payload, which go in vain. And then generally we say that this was the modeling problem, this Y2K problem. You might have heard it created a lot of jobs. So what was the year 2K problem? So when people started writing the software in 70s, or okay, or 70s rather than, okay, so memory used to be very scarce resource. It was not in as abundant as it is today. So like today it's very easy to say that 2 terabytes, 1 terabyte memory is available. uh, okay, that means this much memory as secondary memory, we can say, is available with most of the systems. Okay, and you might have heard about Bill Gates saying 64K is more than enough memory for any software uh, in the future. And this was somewhere in 70s only. So 64K. And you might have not seen, but I have seen the days when 2 GB hard disk used to be a luxury, and it used to be on the servers only. And these hard disks used to be 520 MB, something like that. In MBs, hard disks used to come generally. It's not long back. It's even in the 90s. It used to be the case. Okay. So at that point of time, because memory was a very scarce resource, people kept the date, okay, in DDMMYY. What I mean by date will be 2 digit, uh, month will be 2 digits, and year will be 2 digits only. Okay, so that means if it is 71, so you are not going to write it 1971. It is going to be 71 only. Okay, but nobody thought about that what will happen when year 2000 will come, because then it will become 00, isn't it? Last 2 digits will become 00, and most of the calculations are going to fail. Reason being, if you are going to calculate a certain person's salary or certain things, then you are going to subtract the year, isn't it? From you have deposited the money in 71, and then you are going to get it out on 81. So this money was for actually 10 years, 81 minus 71. But in 00, actually there was a lot of problems. So this is supposed to be one modeling problem which had the modeler seen ahead that sometime after 30 years we are going to be in year 2000. Then what will happen? Okay, then this problem would not have been occurred. But there were a lot of employment for this, and in the COBOL software and in any software where dates were of, that means years were written in 2 digits, has been actually changed into the 4 digit. And all this actually took a lot of time, a lot of cost. Okay, so this was a modeling error or a modeling problem, and how costly modeling problems could be, you can imagine by this. Okay, so these are the things probably you can think of as motivators for understanding or for learning this particular course also. Okay, then we come to look at precisely what are the formal methods. So as far as formal methods is concerned, it's nothing but the application of logic to the development of correct computer system. As I said, you are going to apply the logic or you are going to apply the mathematics for developing the correct computer system. And this correctness is basically viewed as two separate problems. One is the verification and another is the validation. Okay, so every time at least one question you are going to get is what is the difference between verification and validation. This is known as V and V methods, verification and validation. Verification is basically nothing but it says, are we building the product right? Okay, verification says, are we building the product right? That means what? That certain product has been decided to be built, and once you have started building this product, there might have been a certain requirements, and looking at the requirements, you are going to implement, or you are going to make a system, okay, by certain language, and then you are trying to find out whatever system you have made, whether the requirements are going to be satisfied by that system or not. So there will be certain requirements, certain things has been asked to be done, and then whether you have done it correctly or not, that's the only the verification does. Okay, so if we are going to use the logic to help us ensure that the product build faithfully implements its specification, okay, then this is the verification. So verification is basically that if I want to make you understand, supposing you verify, or somebody verifies, supposing you have your original degree, and then you have got a Xerox of your original degree, then any gazetted officer can sign on that Xerox copy of your original degree, that okay, I have verified this. That means because you have got the original, and then from the original degree, I am seeing that that this Xerox is actually a valid Xerox of the original degree. There is nothing, there is no manipulation into the Xerox. Okay, so that is the kind of verification. And validation means, are we building the right product? That means it questions that whether whatever we are doing, whether it is right or not. Okay, so always remember that in the life also, if you are doing things right, that is one thing. If you are doing right thing, that is another thing. Doing things right, maybe there is going to be some thief. If he is skilled, okay, so he will be doing whatsoever theft he is doing very cleverly. Okay, so if he is going to do it very cleverly, then probably from the point of view of the verification, it is achieved. Okay, but as far as the ethics is concerned, whether he is doing the right thing or not, then we can say no, he is not doing, theft is not actually the right thing. So building the right product is actually, once you have actually captured the requirement and build the product, then you are going to again look into the market and ask the people whether whatsoever I have made, whether it is valuable for them or not, whether it is actually making their life better or not, something like that. That's the validation. As far as the mark sheet or your degree is concerned, your degree is going to be validated by the institute itself. Supposing you are going to apply somewhere in some US university, then you have given your transcript over there, then what's going to happen is that university is going to send your documents to the MNIT Allahabad to validate it, whether it's a right document or not. In the past, there has been a lot of cases, people have the fake degrees, okay, and they have done certain things, and they are at sometimes they are at very good positions, but when their degree comes for verification in MNIT, sorry, for validation in MNIT, then it is found that they have never attended the MNIT. Okay, so that is the validation. So this is how we are going to validate the thing. So can we use logic to help us ensure that the specification is complete, consistent, and accurately captures the customer's requirement? So that means, as far as the validation is concerned, so I hope you might have understood verification, building the product right, and validation, building the right product. Always remember, right product means whether your degree itself is a valid or not, and product right means whether the process some gazetted officer has done, whether he has used your original degree to verify the Xerox or not, that is going to be the verification. So always try to differentiate between verification and validation. And then this definition has been actually given by Barry Boehm, where he actually specified that verification is to establish the truth of correspondence between a software product and its specification. It has been derived from the Latin word veritas, which means truth. That means establishing truth. Okay, between what? Between your original degree and between the Xerox. That means there is no uh, mismatch between the original degree and Xerox. Okay, and validation to establish the fitness or worth of a software product for its operational mission. Okay, and that is from the Latin word valere. That means to be worth of something. Okay, so this is the validation. And finally, we have talked about are we building the product right? Are we building the right product? Okay. So in formal methods, if we are going to apply it in the software engineering or SDLC, then we can say we generally have looked at this diagram during the object-oriented modeling course also. So you see there will be some domain. In the domain, certain problem exists. And then for that problem, we are going to write the specification. After writing the specification, we are going to design the solution according to that specification. So we do application design, framework design, or architectural design. And then based on the basis of that design, we are going to have implementation. Okay, so there is going to be analysis, I can say requirement analysis as far as the specification is concerned, a specification of the requirements, and then we are going to be having a design. Then designing the solution, after designing the solution, we are going to do the implementation. Okay, and then after implementation, we can do configuration instances, and then probably we can build the system. So if we are going to verify the thing, so we will see like whether a specification has been drawn from the domain or not, whether the design has been done as per the specification or not. So this is going to be verification. But whatsoever end product is going to be there, that system is going to be validated, or in any stage, design or implementation, okay, or specification or domain can be validated with the end user, whose needs actually are supposed to be modeled as well as implemented by the software development life cycles. So market and users are actually going to be the real deciders for the validation of the software, whether the software is valid or not. Okay, and amongst the developers, there are going to be the various verifications. I hope it has made the I have made it clear that what is the validation and what is the verification. Then finally, why use formal methods? Formal methods generally we use for these reasons. Generally nowadays they are required by the contract or by law. Certain governments, UK, US, actually need that whatsoever softwares are going to be used in life critical systems, they need to be formally verified. So law or contract requires this. So if it is not verified, then probably you cannot use that software in certain life critical applications. Okay, and they are expected to save development cost also. So if it is verified already, then it is supposed that there are going to be few changes into it which are going to be made later point of time, hence it is going to save the cost. Okay, and the product cannot be made sufficiently reliable otherwise. If you are not using the formal methods, then we can say like there are certain bugs which could creep, or there could be a certain bugs which can be there into software itself. Okay, so as far as the formal specification is concerned, we will say formal specification is an example of formal methods applied to software specification verification. Sorry. So formal specification means we are going to formally specify the requirement. We are going to specify the behavior of the system. We are going to write the specification of the system. Okay. So I'll give you a simple example of a specification of a system. Okay. And then I'll give you the example of the implementation of the system. So you might have studied this DFA. Okay. So in case of deterministic finite state machine, if you look at the regular expressions, so regular expressions are supposed to be the specification of any system. Okay. And corresponding to every regular expression, you can make the DFA. You know, for every regular expression, you will be able to make a DFA. That deterministic finite automaton is going to be supposed as an implementation of the system. Okay, so specifications are going to be written, which are going to be short and concise, and then implementations are going to be there for that specification. And implementation should be such that your specifications are going to be met. Okay, so you might have been given certain exercises during the automata theory course that here, look, here there are going to be certain regular expressions and you have to make the deterministic finite state machine. Okay, so if you want to be further clarified on this, then you can think of when you are going to write scanners, that means for the languages in compiler design, then scanners are supposed to be reading the regular expressions, and then okay, then what they are supposed to do, they are supposed to generate the finite state machine implementations for those regular expressions. Okay, so there are going to be certain tools also you might have used in the automata theory lab, that is Lex and Yak, where Lex, input for the Lex is going to be certain regular expressions, and output from that are going to be certain DFA implemented with that. Okay, so this way you can think of a specification as well as implementation. So this is nothing but the language of logic provides an unambiguous method for recording the specification. So we will see the logic, one logic we will see today itself, that how we are going to record the specification, and then the process of writing formal specifications definitely helps uncover any ambiguity and incompleteness into the system. We can then reason about a formal specification to check that the system specified will possess other desired properties as well, which has been actually specified into the specification. So formal specification techniques can be partitioned into two ways. One is the algebraic specification, then model based specification, and then third one is also for a specification is going to be there, that is theorem provers are that means there is going to be a certain premises, logical statements also can be written. Okay, logical statements means that means you can write statements into the first order logic or into the propositional logic for this particular thing, and then finally you can prove that these whatsoever premises you have written into the first order logic or into the propositional logic, they are going to be concluding something. That conclusion could be considered as a final outcome or the final behavior of that particular system, which should be supported by that particular system or that particular model. Okay, so algebraic specification, that means in that there are going to be certain set of actions, and your system is supposed to be defined in terms of the actions, and combination of the actions and variables are going to be represented by certain equations. We will see after a few minutes that how we are going to write these algebraic specifications. And then model based specifications are also going to be there. Here the object to be described is a model in some expressive logic. Okay, and if this model based specification, we will also see today, just in few minutes. Okay. So, and then finally, formal verification is nothing but an example of formal methods applied to verification. And this is nothing but the process of constructing a proof that a computer system will behave in accordance with its specification. So first you specify the system is going to behave. The standard verification techniques is testing. Okay, remember. So there are at this point I need to clear to you there are certain similar things to the formal verification or formal methods, that is the testing and simulation. Okay, so as far as the simulation is concerned, that means you are going to simulate a certain system for a certain behavior. Okay, so always remember, you can actually simulate bigger systems. And finally, first of all, you can think that testing can be done for any system. Okay. But remember, testing always shows the presence of bugs, but never shows the absence of bugs. If you are testing, that means you are trying to find out certain bugs into the system. Okay. And if you are going to do the simulation, then definitely whatsoever implementations you have done, for all those implementations, you can write test cases and you can do the testing for finding the bugs into the system. But for smaller systems, which cannot be actually cannot be you can say the systems which are smaller in size, for them you can write the simulations also, and which are actually safety critical systems. So all implementations cannot be simulated, you remember, while testing can be done for any kind of implementation. So as far as the verification is concerned, this is again going to be a smaller set. You cannot verify a very large system. Okay, even whatever systems you can simulate, you cannot verify them because verification is very costly. We will see there is a lot of problems in verification. Like if we are modeling model based verification, we have state space explosion, which we will see later on. Even in theorem proving, it costs a lot. So there are not going to be a lot of well established tools which can verify the very big systems. So generally what we do is whatever we can implement, actually we can test. But whatsoever we can implement cannot simulate. Whatsoever even we can simulate cannot verify. So remember, so verification is going to be done for safety critical applications. Always remember, where you think like if something goes wrong, then it's going to be affecting human lives or affecting whole of the system a lot. So for a smaller part you can verify, but you cannot verify for all the big systems, remember. Okay, so in the formal verification process, actually what we are going to do practically, if we are going to do, then describe the property which we want that should be there into the system. We will be describing the property and we will be describing the implementation. As I said, you will be describing, we may be describing the property if you by regular expression, and then you may describe the implementation by DFA. Okay, then we can construct a proof that whatsoever regular expressions are going to be there, they are being taken care by the DFA also. Okay, so you know, in there is a clear-cut rules how you are going to convert the regular expressions into DFA, how you are going to convert the DFA into the regular expressions. I'm sorry. That means if you have followed those rules, that means you have done your description. That means you have done verification properly. Okay, so in formal verification, it requires basically a language for describing both specification as well as implementations, and then there should be a deductive calculus which is going to establish the truth that from a specification I can actually reach to this implementation. Okay, so that's all we will be trying to do in this particular course and today also. Okay, So it's just an hour. So if you want, anybody want, we can have a break. Otherwise, we have come to the point where two things has to be done. One thing is like we have to build an implementation, which is actually going to be done by the model. And another thing is we need to write an specification that is going to be written through a certain logic. So we will look at a very small system and try to model that particular system. Okay.